Okay, here's a tutorial in English as requested on how to draw the shear and bending moment diagram for a simply supported beam with some kind of loading. So let me try to draw quickly the beam I'm talking about. So we have a beam like that, two supports, hinge on a roller, and we have a distributed load on that end, and we have a point load here, and these are the dimensions. Okay, let's put some numbers here. Okay, first I have to label this as A and this as B, and the load here is 4 kip per foot, and we have 8 kips. Okay, how to draw the bending and shear moment diagram for this beam. First of all, we need to find out the reactions or the reaction forces in the support. So in order for us to do this, we need to basically apply the three equilibrium equations, which are the summation of the forces in the x direction should be equal to 0, the summation of the forces in the y direction should be equal to 0, and summation of the moments about a point should equal to 0. And again, our sign convention is gonna be like this. This is the positive x in this direction going to the right, upward is the positive y, and the rotation counterclockwise is positive. Okay, let's first draw the free body diagram for this beam. Oh, I forgot to put the lengths here. So we have, let's see, let's say this is 4 feet, 2 feet, and 2 feet. Okay, the free body diagram for this beam should look something like this. Okay, that's the beam. Okay, what kind of reactions do we have at the hinge? At A, we have AX, we have AY, and of course here we have a BY. Okay, and from this one right here we do have 8 kips, and remember, to calculate the reaction forces we need to concentrate all the distributed forces. So how to concentrate this load or distributed load is just simply by multiplying the value of the distribution by the length of the distribution and placing the new point load in the middle. So it's gonna be somewhere in here, and it's gonna be 4 multiplied by 4, that's 16k. So now we're ready to calculate the reactions. Okay, let's apply the equations. We have sigma of the forces and the x equals to 0. Okay, let's look here. We only have ax, so it's ax. If I'm doing the summation, I put a plus and carry on, but since there are no force in the x direction but this force, I'll end up having that equals to 0, and it's very straightforward. Okay, for the second one, it's going to be sigma Fy equals to 0. Now, couple of ways of doing this. You can go force by force, counting 1, 2, 3, 4, or you can do the bottom one will equal to the top one. Let's do it one by one. It's gonna be clear for everybody. So it's AY going up, that takes care of this one. Then we have a 16 going down, that's why we have a minus 16, then an 8, minus 8, then we have a BY going up, so that's a plus BY, that's gonna be equal to 0, or simply it's gonna be AY plus BY equals 24. Now let's try to apply the third equation. The third equation says sigma of the moments about a point is equal to 0, and just let me remind you, this is the positive direction. Okay, let's pick a point here. There is no rule of picking a point, but the thing is, the best thing about picking a point is trying to pick that point that have some forces passing through it, so you cancel one of the unknowns. So basically I can pick this point A, so AX and AY does not, or they don't play any role in the moment equation. And if I pick BY, that means BY does not, and the AX, of course, it passes through the point B. Both of them, they don't come into the equation, so it's up to you guys. It's gonna be A or B. I usually do A. It's just an old habit I picked along the way. Anyway, so it's gonna be the summation of the moments about point A equals to 0. So let's do this. How can we do this? The way I do it, I go the opposite direction and start from there. So if I'm summing the forces, the moments about this point, I start with the furthest force on the beam. So it's going to be by multiplied by this distance. Then I'm going to have 8 multiplied by that distance. Then I'm going to have 16 multiplied by that distance. So by multiplied by the whole thing, which is 2 plus 2 plus 4, that's 8. So by multiplied by 8, so it's going to be 8 by. Let's just double check on the direction. So by is rotating this way, so it's positive. Now the 8 is multiplied by that distance, which is 2 plus 4, that's 6. So it's 6 multiplied by 8, or should I write it the other way around so it's gonna be clearer for you guys? Okay, so it's gonna be the force 8 multiplied by the distance, and the direction is gonna be this way, so it's gonna be a negative, and that's of course is a positive. So put a negative here. Same thing goes for the 16. 16 times half the distance. Remember, the concentration of the distribution or distributed load is at the middle of this portion of the beam, which is 2 from point A. So it's gonna be 16 multiplied by 2, and that will give me equals to 0. But again, what is the sign here? Obviously the 16 will rotate this way, so it's a negative, so I put a negative here. And using this equation, I can solve for by easily to be 10 kips. Now I have a value for by. All I need to do is just go back right here and substitute it back in this equation, and I can find the value for ay. And if you do this, very easy to do. So what is the ay? If I add by, which is 10, is going to be 24. Obviously it's just basically 14k, and that takes care of the reactions. So that's step 1. Step 2 is try to draw the shear diagram. The shear diagram is the key to the moment diagram, so if you do the shear diagram correctly, the moment diagram shouldn't be a big problem for you guys. So let me just scroll down right here. Okay, and what do we have here? So I have, that's gonna be my beam. Okay, the points I need to consider at the shear. Of course, I need to know where to start and where to finish. And now the new point is going to be the beginning and the end of the distributed load. These are key points. So the beginning, is this one, and the end is right here. The other points I need to consider is any point where the point load is applied, which is that point right here. Okay, so that's another point here. I need to get the values of the shear at these points. If I do that, I will have a complete shear diagram. How does this thing go? Okay, at 0 we have a force going upward. You guessed it, it's AY. AY is going upwards by a value of how much? AY is 14. I'm just gonna stop writing K's here just to make this quick. Okay, now the tricky part. What does it mean to have 4 kips per foot along this floor? What that means basically, let me just draw it like this. So if one foot will have a 4, the other foot have a 4, the other foot have a 4, and so on. So basically what this shear diagram can tell me, or what I can get from this distributed load, is the following: that this thing will start to descend at a rate of 4 kips per foot. Okay, what is this distance? The distance of the distribution is 4. So for every 1 foot I will go down 4 kips. So what happens at 4 foot? How many kips I should go down? That's the answer basically to the value of the shear force here. So I'm starting with 14 and I'm going down at a certain rate, which is 4 here. So 4 by 4 by 4 will get me the value over here. But I have to keep in mind that I'm starting from 14, so 4 by 4 is 16. So the total descent value, let's just call it this, descent value is 16, but I'm starting with 14 in the positive direction, so that means I'm gonna end up somewhere in here with a -2, and I have a straight line. Okay, now this one's done, this one's done. Now between here and here, do I have any forces on the beam? No. So if I don't, my shear diagram should go horizontal just like this, straight. Okay, at this point right here I have a 8 that's going downward, so I should just make a straight line, 8, and I ask myself again the same question: is there any force between this point and this point? No, so I should go straight. Now what do I have at B? I have a BY, which is 10. So let's see, where am I right now? I'm down here, which is 8 plus this. You can think of it as -8. So it's -2 -8. So the total value, or the total distance between this line and this line, is 10 in the negative. So I'm going, BY is another force that's going up. It's right here, this force, which has a value of 10. So I end up at 0. So I start with a 0, I go up 14, descend to this point, nothing happens here. I go down straight, -8, nothing happens here. Then I go up with a -10 value. So I start with a 0 and I end up with a 0. So now we have the shear diagram. Let me just tell you this. What is the relation, or let me ask you this, what is the relationship between the shear diagram and the bending moment diagram? Well, there is a theory behind it, no doubt about that, but I mean, just to do it quickly in an exam, the way you think about the moment diagram, all the values at the moment diagram are just simply the areas underneath the shear diagram. So if I have a way of calculating this area as a positive area, and then calculate this area, and then calculate that, and then calculate that, I'll end up having the whole bending moment diagram. Okay, so again, what are the important points now? Of course, it's the beginning and the end of the beam. Now, of course, these points I put on the shear diagram, they should go down as well. Any new points? Yes, this point is of great interest to us, where the shear just intersect with the x-axis is a great point to study right here, and that's gonna actually, this one's gonna give us most of the solution, and this is the tricky one basically. Okay, so as I promised you, if we calculate the areas under the shear diagram, we should get some values here. Okay, so the value at this point is the value of the area under the shear diagram for the whole shear diagram before that point. Okay, what about at this point, which correspond to this one right here? The value of this area plus the value of this area will give me the value of the moment at that point. Okay, what about this one, which correspond to this one? It's the value of that area plus the value of that area plus the value of that area, and if I sum them, I'll get the value of the moment diagram at this point. Keep in mind, this value, the area on top is positive, and all the values of the areas here are negative. Okay, so let's try to find out. It's basically calculating the area of regular shapes like a triangle or a square or a rectangle. But the trick here is, do you know all the lengths of the, for example, the very first problem I'm gonna have is, where this thing intersect? What is this length right here? So let me draw it like this. We have a line, something like this. In order for you to find this length, let's call it x, you know this length. It's the whole length of the distribution of the load right here. It's this. So this is 4. Okay, what about this? This is 14. We do have two similar triangles, this one and that one, but some people will say, hey, how do you know that? Okay, let me draw it this way. So if I just do this, now we have one triangle like this and the other triangle like this, and they are, of course, they are similar triangles. Okay, what is the length of this? It's basically the length of this, which was 2. So it's a 2. Okay, now let me just center this on the screen so you guys can see it. So from similar triangles, what do we know? We can get a value of x if I can use these numbers. Basically, I can say the following: x over 4, which is the base, this one, over the big base, should equal to the 14 over the whole thing, which is the 16. So it's gonna be 14 over 16. That's from similar triangles. Okay, so we solve for x, and if you do this, it's gonna be 3.5 feet, and this one's gonna be just half a feet. So we know all the lengths now. Let's try to calculate the area. What is the area of this thing? It's basically 1/2 multiplied by 3.5, the base, multiplied by the height, which is the 14, and that will give me basically 24.5. So at this point, which corresponds to this one, can go up here and say this one right here is 24.5 cubic foot. Okay, what about this one? This one is basically, it's the area of this triangle plus the area of this triangle, keeping in mind that this triangle has a negative area. What is the area of this triangle? It's going to be 1/2 multiplied by the base, which is again 1/2. Let me write it this way so you know. And again multiplied by the height, which is 2. So 1/2 times 2 is 1, 1 times 1/2, so the answer is 0.5. A negative 0.5. So if I added the area of this triangle and this triangle, I'm just basically saying 24.5 positive plus negative 0.5, which just give me 24. So I'm gonna put it like this and say this thing is 24 again cubic foot. Okay, using the same logic. For this point, it's just the area of this added to the area of this part added to the area of that part. Okay, so what is the area of this? It's this distance multiplied by this height. This height is 2, or negative 2, the other way. What about this thing? Okay, it's the distance between the end of the distributed load to the beginning of the point load. Just let's look at the problem. It's this distance right here. It's 2. So the area here is 2 times 2, which is 4. But again, it's a negative area, so it's a negative 4. Okay, so I know now that this area is negative 4, so I have a new area of negative 4. I should add this area to that and to that, which is equivalent to just adding it to this, because this is basically this area plus this area. So basically I'm subtracting 4 from this one, so I should end up having 20 cubic foot. Okay, and what about this one? It's again 2 multiplied by minus 10, which is minus 20. I add it to the previous value, which is 20. So minus 20 plus 20 will give me a 0. And that's a check for me that I did it right. Why? Because I was expecting the moment at the hinge and the roller to be a 0. I started up with a 0, got a couple of values, and they should add up to 0 right here, because at the pin support right here there is no moment, or the moment equals to 0. Final step is, how do you connect these lines or these dots? Okay, let me show you something. So I have a beam, have a middle point, have a point here, and a point here, and a point here. At this one, I have 24.5. I'm just skipping the units for now. At this one, I'm having 24. And then this one I got 20. And of course I start with a 0 and a 0. Here's the rule. If it's all depending on the shear diagram, and this is the moment diagram. So let me put it this way. If your shear diagram was straight line horizontal, your moment should be a straight line going up or down. If the shear diagram was going down and up, your moment diagram should be parabolic. Okay? It has to do with the one is the integral of the other, or if you differentiate this, you'll get the other. So I'm just skipping the theory behind it, but you can write it this way for you, just to remind yourself that if the shear diagram had a straight line, that means the moment diagram should have a straight line going up or down. I'm not claiming here it's going up or it's going up only. It's going up or down. And if the shear diagram is an inclined line, or going down or going up, so the moment should have concavity, right, like this. So let's apply these rules. Okay, let's take a look. It's very quick. So from this point right here to this point, I'm having a straight line, but it's declining. So I'm in this category. So what should I get? I get a parabolic, or a curve. So from here to here is gonna be something like this. So it's not a straight line. Okay, now between this point and this point I have straight line which is horizontal, so I'm gonna have a straight line. And from this one, I'm sorry, this one's wrong, forgive me. Okay, again, from this point to this point, it's basically from this point to this point, so it's the whole thing like this. Okay, it's still a declining straight line which is from here to here, so it passes through 0, the intersection, and this point which is on here is going to be 0, the intersection, and this, so the whole thing is a curve. Okay, between that point and this one, it's going to be a straight line here, horizontal, so this one should be straight line again. I'm sorry, I'm just a little bit not that accurate today, I don't know why, but let me try it this way. Okay, that's good. And again, for this one, it's gonna be just a straight line like this. So here you have it, the moment values. This is the moment diagram, and this one up is the shear diagram. Okay, so again, first you have to calculate the reactions like we did using the equations, 3 equilibrium equations. We will get the reactions. Okay, then you draw the shear diagram. After you get the shear diagram, try to get all the lengths of the segments of the regular shapes, as we said, the triangle or the rectangle or the square, and use the trick of similar triangle to find the unknowns, like in this one. Calculate the areas, then basically the points or the values of the moments are basically the areas added up together up to the point you are interested in, making sure that anything that's above the x-axis is a positive area, and any area below the x-axis is going to be a negative area. So that's how we do it, and basically if we follow the same logic, we can do the moment and shear diagram for any beam. Good luck with that, and I'll see you in another tutorial.